So then let's go to 6.3. Now it's more corresponding to quantum mechanics because we talk about the Hermitian operators are important in quantum mechanics. So basically now you are dealing with operator H Hermitian, that's H itself, right? And then you try to solve the eigenvalue problem using this Hermitian operator. I mean, the notation is kind of a mixed notation because all these C are supposedly components are based on a certain basis. But then your text will also use this bracket notation. So it doesn't matter. Okay. So, assuming you have a basis, then you get a set of coefficients C and change that to a matrix eigenvalue problem, but still keeping using the bracket notation. So the eigenvalue problem becomes H and the C sub I. Just keeping in the possibility that there are more than one eigenvector and eigenvalues, right? And it can be infinite number of them, lambda I, Ci. This is the eigenvalue problem for this Hermitian operator. And so we want to do two things. One is to show that all the eigenvalues are real. The other is to show that the eigenvector corresponding to this eigenvalue are orthogonal to each other. Okay, so there are two things. The first thing is just introducing another vector. But these i's are the index for the eigenvalues. So this is not what we did before, not the basis, not the index for the basis. Right? So we have another eigenvector C sub j corresponding to lambda sub j, C sub j. And first, we assume that the for I not equal to j, lambda I is not equal to lambda j, that's non-degenerate. But then we can then generalize to the case of degenerate case. But we'll do the non-degenerate case first, right? So we now take the scalar product, the C sub I and j between like this one, C sub j and H, C sub I, right? And now this is, let's substitute this in here, so it's lambda I, C sub j, C sub I. And this is not zero, even I not equal to j, because these things are not normalized. We don't know if they're normalized yet. So we'll keep it general. Right? Say that again. We'll show that they are orthogonal, but later on we'll show that they are orthogonal. But then we'll keep it like this for notation-wise, right? And then we'll do the same thing for the second equation, but doing the scalar product C sub I, H, and C sub j, which using the second equation becomes lambda j and C sub I, C sub j. Right? And now the idea is you can try to make this the same direction because they're not the same here. There's one is j and I, the other I and j. And what we can do is like for we can take the complex conjugate of this equation, like the complex conjugate of this equation, and now that becomes complex conjugate, right? The second equation, take the complex conjugate, and then we can reverse the order of that, right? And yeah. But before we reverse the order, because we want both a j and I, before we reverse the order, we use the property of the adjoint for the left-hand side, because x operates on this one. I mean, like before we talk about, we don't have the second bar, but imagine there's no second bar. This x will move to the other side, become x dash here. C sub I, C sub j. Right. And now you use the property that C dash is this, H dash is just H, right? So that equals to H C I C sub j complex conjugate. And then again, now we use the scalar product, so we can reverse the order and get a complex conjugate out. So get rid of this complex conjugate. It becomes a Cj H Ci. Right. So that's the left-hand side of this one. The right-hand side, we can do the same thing. Keep the arm of J's complex conjugate. Just reverse the order by the property of scalar product. Cj. Right. Now we see that this and that are the same. But the right-hand side, the scalar product are the same. The eigenvalues are not the same, so you can subtract one from the other. This implies. Wait, we don't do that yet. We need to argue about one thing first, that the eigenvalues are real. And to argue about that, that is because the two equations are actually exactly the same. So these two, so basically, if I mean it's exactly the same if we choose I equals to j. So we can choose for I equals to j, right? Then both the left-hand sides are C sub I, H C sub I, and the the right-hand side is lambda I, C sub I, C sub I, there's lambda I complex conjugate. For this one, C sub I, C sub I. Right? So just setting j equals to I, then from this equation, you imply lambda I equals to lambda I complex conjugate, because this is non-zero. The scalar product with itself is non-zero by definition, except that when it is zero, exactly zero. For non-trivial case, obviously, that is not the case. So this is finite. The only possibility is lambda I equals to its complex conjugate, meaning it's proposed. Yeah, real. So all the eigenvalues are real. It's okay. That's it. And this is for all I. So any number of eigenvalues, they're all positive. They're not all real. They're all real. Okay. All right. So that's the first step. Now the first step is for I not equals to j. I not equals to j. That we go back to this, but then we get rid of the complex conjugate because it's yeah, they're real, so you don't need a complex conjugate for real quantity, right? Now you use this equation, this equals to this equals to this equals this, and you get lambda I minus lambda J, Ci, Cj, Ci, Cl. Okay. Now consider the cases that they are non-degenerate. So if lambda I not equals lambda J, that implies C sub J, C sub I is 0. Okay. So the second conclusion is if the eigenvalues for I and J, they are not degenerate, then if I not equals to J, then the eigenvectors are orthogonal. Okay. So the second case, and the case when the lambda I equals lambda J for degenerate case, obviously this equation already satisfies, so you don't have the automatic orthogonal property like that. So this can or cannot be of 0, the second factor, the scalar property. But then if you have two vectors, C sub I and C sub J, so you can always write C sub I prime equals the combination of like a C of alpha C sub I, like beta C sub J. In this case, they all correspond to the same eigenvalue. So the C sub I prime also is the same. It's also an eigenvector for the same eigenvalue. So you can require that the C sub I prime, say C sub I prime, C sub J, and C by choosing appropriate alpha and beta, which is straightforward to do. You can choose instead of I, C sub I, you can choose C sub I prime, and then make them orthogonal. Is that okay? So, that's for the two situations. If you have a degenerate for two eigenvectors with the same eigenvalue, then you can choose two that are orthogonal. And if you generalize that to even more eigenvectors corresponding to the same eigenvalue, you can keep doing that, keep doing this Gram-Schmidt method and define a set of whatever number of eigenvector corresponding to the same eigenvalue. You can define a set of new eigenvectors that are mutually orthogonal. Okay, so that the general idea is you can get the set of orthogonal eigenvectors, and because of that, after you do that, all this method, you can choose a C sub I and then after normalize, you can choose a set of C sub I. And you can choose C sub I such that C I C J is this one for delta. After normalization, for Hermitian operator, you can always find a set of eigenvector so that they are orthonormal. Okay. And that's property of Hermitian operator, and that makes many problems easy to solve, and then it's also also physical because all the eigenvalues supposedly corresponding to the possibility that you get out of a real measurement in physics. Even in measuring a quantum system, all the measurement you wanted to get a real outcome. So all the eigenvalues must be real. It's okay. So let's see how much time we have. All right. So it's okay up to here. So this is actually this section is a central one, 613. It's okay. So that's the argument that for Hermitian operator you can have these properties. It's okay. How this show how the eigenvalues are real, and then so that the eigenvector orthogonal for non-degenerate case, and then you can generalize to degenerate case by using the Gram-Schmidt method. Okay, so that's the whole argument.